Hello everyone, welcome back to Advent of Code 2024. We're going to be doing day 13 today, but as you can see I've already done day 13. So this is going to be a shorter episode because I solved this one off camera and we're just going to talk through it. I'll talk some more about why that is after I've read the problem statement for you. Day 13, Claw Contraption. Next up, the lobby of a resort on a tropical island. The historians take a moment to admire the hexagonal floor tiles before spreading out. Fortunately, it looks like the resort has a new arcade. Maybe you can win some prizes at the claw machine? The claw machines here are a little unusual. Instead of a joystick or directional buttons to control the claw, these machines have two buttons labeled A and B. Worse, you can't just put in a token and play. It costs 3 tokens to push the A button and 1 token to push the B button. With a little experimentation, you figure out that each machine's buttons are configured to move the claw a specific amount to the right along the x-axis and a specific amount forward along the y-axis each time that button is pressed. Each machine contains one prize. To win the prize, the claw must be positioned exactly above the prize on both the x and y axes. You wonder, what's the smallest number of tokens you would have to spend to win as many prizes as possible? So they give us a definition of all the machines, each one being an A button, a B button, and a prize, and the offsets. Blah, 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 and there's a bunch of examples. It's pretty clear that you could just do a brute force search here because all the x's and y's are positive. You never have to you could also they specify here that you'll never be asked to push a button more than 100 times. So you could just do a search for there's only 10,000 possibilities of ways you could push up to 100 buttons on each. Find all the ones that add up to the goal and choose the one with the smallest number of A button presses, basically, right? Because the B button presses are cheaper. I guess that's not quite true. You would have to be a little more careful than that because anyway, you could find all the ones that happen to hit it and sort them by their cost or something of that nature. But this very obviously is like a system of 2 linear equations in 2 variables. And there are well-known methods for solving such equations. I'm not an expert in them, but I can look them up. So the reason that we're doing this off camera, that I did this off camera and we're now getting a summary today, is that I spent forever when I was doing my first draft of this recording while I was trying to solve it on camera. I spent absolutely forever trying to learn all of linear algebra so that I could do this myself instead of just type in some equations from a website. And in particular, I think I absolutely could arrive at the general form of the solution to this is a system of 2 equations. You could replace each of the coefficients and whatever this is called, constants, with a variable and do the variable substitution to, solve one variable in terms of the other and then solve the whole equation in terms of the second variable. So, and then you have solutions to both of them in a general form. I think I could do that algebra. You can also just look it up. It's online, Kramer's method is what this is called and involves determinants and I don't really know what that means, but I do, but I don't know why it works. I assume it's the same thing you get if you do all the algebra. The thing is that only works if the 2 lines are not collinear, right? If they're parallel to each other, the vectors defined by this and this, if they are parallel, then so the reason that you can solve a system of 2 equations and 2 unknowns is because each equation gives you the definition of a line, basically, and 2 lines on the plane intersect at exactly 1 point, and that's the only solution, except if the 2 lines are parallel. If they're parallel and they don't overlap, then they never intersect at all, and there's no solution. If they are parallel and do overlap, then they overlap at every point. They're the same line. And in that case, there could be multiple solutions to make both equations true at the same time. And I spent a lot of time thinking, like, okay, I said, well, like, probably the input only has non-collinear vectors, but I should check. And also, by the way, if these two represent lines, and this is a point that the lines are supposed to meet at, so even if these two lines are collinear, they might not pass through this point, and so there could be zero solutions. But if they are collinear and they pass through this point, there could be infinitely many solutions, assuming you can use, well, I don't know about infinitely many. There could be more than one anyway. I think infinitely many if you allow all positive and negative numbers. Yeah. Positive and if you allow negative integers, negative button presses, there would be infinitely many, but we're not going to. So there would only be finitely many, but non-zero. So I spent a lot of time thinking about and looking up, like, how you solve what's called a Diophantine equation, which is like an equation that's only in integers, where only integers like count as valid answers, and like taking if these equations are collinear, then you can find out if one of them goes through the goal point, then of course they both do, and so that's a single Diophantine equation, and like you can solve it. And the methods I was looking up were very confusing, and I was like having trouble understanding them. And it looked like a lot of work. And eventually I got frustrated and was like, look, let's just check, are any of the machines in the input collinear? And they're not. They're all non-parallel lines. So just doing the obvious thing of looking up how to solve two equations and two unknowns and plugging in the answer will always uniquely give you one solution. It'll give you one solution. Or I guess I didn't actually check that none of them are collinear. None of them are, any of the ones that are parallel happen to also be collinear going through the exit point. Although I think I did prove none of them are parallel at all. Anyway, whatever. So it works to just do the obvious thing of like Google how to use all two equations and two unknowns, and then check if the solution is integers. Actually, I didn't check if the solution is positive integers. I think I might have gotten lucky on that. No, because of course, well, yeah, maybe. Okay, not lucky. If it was luck, it was luck Eric gave us on purpose. But I should have been a little more careful and checked that none of the button amounts are negative. But it turns out that you get the right answer even if you don't bother to do that check. So they all have solutions that are positive in both A and B, it turns out. Or no solution, no integer solutions. So in the end, I spent a bunch of time researching like how, Euclid used to do math. And then finally, like, crumpled it all up into a ball, threw it away, and copied a two-line equation from the internet. And it was not very interesting watching. So instead, we're just going to look at the answer here. I defined a coordinate as a pair of ints. I could use v2, right? But I don't need to do any math on coordinates here, really. So a button is just another name for a coordinate, and a machine, which is what we're parsing each of the problems, is two buttons and a goal coordinate. Of course, I could just make it 3 coordinates, but it's nice to have the types be a little bit more clear about modeling the problem. The main, the workhorse of this whole solution is the determinant function, which takes a matrix, a 2x2 matrix, and gives you an integer result, which is, I'm representing A as the top left, B is the top right, C is the bottom left, D is the bottom right. So A times D multiplies the top left to bottom right diagonal. Oh, need a space there. B times C multiplies the top right to bottom left diagonal. You subtract them. That's the definition of the determinant. And the method for finding the solution to a system of two equations and two unknowns is to get the determinant of the coefficient matrix, the A's and the B's. That's our D here. Now, obviously, I never actually construct a matrix. I just pass around 4 ints. This is like sort of sloppy, I guess, but a lot easier than constructing matrices just to tear them apart. So you find the determinant of that, and then you substitute the constants, our goal, where the prize is. You substitute that in for the A variables, and that's what I call dA. You take the determinant of that. Then you substitute the coordinates in for the B variables instead, and that's your dB. And the solution is to divide dA by D, and that's the A position of the solution, and divide dB by D, and that's the B position of the solution. So I say first, so this whole thing doesn't work if the determinant is 0, which is what happens when the lines are parallel. So we have this check here saying if it's 0, there's no solution. And then saying when you divide dA by D and dB by D, I'm using div mod here, which gives you the quotient and the remainder. If the remainders are both 0, then great, return both quotients. Otherwise, there's no solution. Or there was a solution, but it wasn't at integer coordinates, and so that you can't push a button half the time. And that's pretty much all the math here. The other thing to do is to parse the input, which is what prepare does. So we use textreg explicative. I say an input is many machines optionally followed by a new line. Or many copy, yeah, each optionally followed by a new line. Because in the input, each machine has a new line before the next machine, a blank line. So that's the optional new line. This is one case, by the way, where textreg explicative lets you not worry about a problem that you would have had if you were using parsec, I think. I think that's true. You'd have to be more careful in parsec, or in any of the popular parser combinator libraries. Because when they have consumed some input, they generally refuse to give it back. They don't do backtracking unless you specifically say you should backtrack here. And they only backtrack sort of locally within the scope of a single thing. And like, I don't know. I guess you would put I'm honestly not sure where you would put the optional if you're using parsec. Textreg explicative, because it doesn't offer you any monadic combinators, can use a search method that implicitly backtracks without being tremendously inefficient. And so, and it still finds like the one match, or it finds one of the matches, and there will be only one in our grammar here. But it'll consume this new line, but be willing to sort of give it back. It's not actually backtracking. It's like trying different things simultaneously. But so my first attempt to parse this failed to parse because the last machine has a new line after it, of course, but it doesn't have an extra new line making space for the next machine. So maybe what you would do to solve this problem is you would put an optional new line before the machine instead of after it. Yeah, that's probably what you would do. And that would work because parsec would say, oh, well, there's no new line here. I'll just not parse it for the first machine. And then for later machines, it would say, oh, look, this machine starts with the new line. So anyway, but you'd have to be more careful about it with parsec. Here I just can throw an optional new line in kind of any place where I was looking for a new line. A machine parses 3 lines, one labeled button A with plus, one labeled button B with plus, one labeled prize with equals, because Each line is kind of a label, an X, and an operator, which is plus for buttons and equals for prizes. And then like similarly, so I had to say like explain how to parse those two kinds of lines. Right, button a line of button A and plus, a line of button B and plus, and a line of prize and equals. So line is a function that takes a label and an op and gives you back a regex. And it just tuples up like a bunch of annoying punctuation-laden gobbledygook, with the result that it throws away the characters we know are going to be there and just parses out a decimal. And so there's the solve function, which I wrote first. I called this function part 1, and then when I read part 2, I just factored out the entirety of part 1 and called it solve, and then did something else for part 2, which we'll see in a sec. Part 1 is just solve a sum mapping the score over map maybe of win, because win returns optionally a coordinate, maybe a coordinate. So for each machine, you try to win it. If so, you score that win and add up all the scores. And the score is just 3a times b, as defined in the problem. Any machines you can't win, map maybe will drop, and so you won't end up scoring them. So what's the deal with part 2? Where are we? Part 2. Oh, you discover the clause nowhere near where you expected it would be. There's a unit conversion error. The position of every prize is actually much higher on both the x and y axis. So this is to punish you if you tried to do the brute force approach. Make you realize there was something smarter you should have done. But since we were just solving a system of equations, it's quite simple. I just say part 2 is solve, but first shift the goalposts on all of the machines by this amount. Shift the goalposts takes an amount and a machine, and leaves the A and B buttons alone, but adds the amount to the prize position. And that's it. So, I don't know. I wasn't satisfied with my attempt to solve this. I don't know. Like, am I upset at the problem? Kind of. Because, like, there absolutely could be machines defined that have A and B buttons that are parallel to each other, or whose vectors are parallel, some of which are solvable and some of which are solvable with multiple solutions and some of which are not solvable at all. And I feel like, if they're not going to give you in the problem statement some assurance that the problem has a unique solution, I kind of don't like that an implementation that doesn't address that potential uncertainty. Like, I don't like that works. But also, it's like way too hard for me to figure out how to handle the uncertainty. So in the end, I just like caved in and did the obvious easy thing. And I don't know, wasn't very happy either while I was working on the confusing part or while I was like typing in the solution to the easy cases. So, yeah. But I did want to get out a video, like at least summarizing the solution. Stay in the habit of, getting them up and see how long I can stick around this year. Hope you guys enjoyed. Thanks for watching, and I'll see you next time.